Hi, today we're gonna do a quick experiment. It's a pretty classic experiment looking at a piece of metal and trying to figure out the specific heat capacity of that metal. So what you need for this is some piece of metal that's hot. We're gonna start off with the metal in an oven, and then we're gonna take some water and I'm gonna walk you through it and the calculations and see kind of how we use the principles of thermodynamics to determine something that's unknown about a piece of metal. So just a quick word, the principle behind this experiment is if you have a piece of metal, okay, you'll see the metal has a little knob on the top. This is my unknown metal, and I don't know what the specific heat capacity of this is. So C metal is my question mark. If this is hot, and I want to figure out something about this, I need to get the heat from this metal into something else that I can measure. And typically, because you can't measure heat directly, there's no heat meter, but we can measure temperature. And so if I have a container and I have water in it, so water is something that we know lots about. We know we can measure the mass of the water, we can measure the temperature of the water, we know the specific heat capacity of water. So the specific heat capacity of water is 4.2 joules per gram degrees Celsius. That means it takes 4.2 joules to heat up 1 gram of water by 1 degree Celsius. If I take this metal and put it into the water, and this is an insulated container like this, then once that metal is in the water, all that heat should go out into the water. And when that transfers energy, I can measure the temperature of that. So the temperature should go up. And if I can figure out how much energy goes into the water, well, I know that that energy came from the metal, so then I can figure out something about the metal. So that's the principle behind this calorimetry experiment. We want to do it in a controlled environment, and so we're going to try it and do this right now. Okay, we're going to start off with an insulated container. So you can either use a styrofoam cup. I have this little thermos here. I'm just going to put it on a scale. We want to get measurements of the water, and mass is the best way to get the measurement of the water because volume is not as accurate. The scale is much more accurate. So we're going to zero the scale. I'm going to get some tap water in here. And you generally want about, depends on what kind of container you're using, but you just want enough water that you're going to cover up the piece of metal completely. So in our experiment, we need about that much water, about 80 milliliters, or in this case, 82.91 grams. So we'll go ahead and measure that. I'm also going to measure the temperature of the water. So this is this in here, and get that to stabilize. And so we're at about 21 degrees Celsius for our water starting temperature. 20.9. Okay, there we go. So now I'm gonna walk over here. This is our oven. Our oven inside has some hot metal, and the current temperature of the oven is about 100 degrees Celsius. So the oven's at 100 degrees Celsius. I have my water next to me, so I wanna make sure that's ready to go, and the thermometer is in it because I wanna get the temperature of the metal and the water as they reach thermal equilibrium as directly as possible. So I don't want to lose any heat to the atmosphere. I don't want to get the metal right into the water. So I'm going to go ahead and open this up. This is our piece of metal right here. I'm going to take this, put this into the water. I'll make sure it's totally covered, so I turned it sideways. So all the heat goes into the water, and you can see the temperature of the metal and the water. Okay, Okay, so we're at about, sorry. I'm just gonna stir this up to kind of make sure the water temperature is evenly distributed. So it looks like 24.2 is our maximum temperature. That's when we have reached thermal equilibrium. The metal and the water are going to be at the same temperature because they are in this container together, and so they are reaching the same temperature. And so that's what we're going to call our thermal equilibrium temperature. Okay, now I'm going to come back over to the scale. I'm going to take the metal out. It's cool to the touch. It's only 24 degrees. I'm going to dry it off. So make sure you don't have any water on the piece of metal. And I'm going to go ahead and weigh the metal. Never want to weigh hot metal, so do this after you're done. It's always easier. And the metal is 57.27 grams. 26. Okay. Okay, so here are my data. The way I like to do this problem is it's two things happening. You have water, which is cooling down. Sorry, water is heating up, and it's going from 20.9 to 24.2. Then you have your metal, which is cooling down. The metal is going from 100 degrees down to the same temperature, 24.2. So this is what we call thermal equilibrium, and they reach the same temperature. And the first thing we gotta do is write what I call a Q equation. The Q equation, Q is heat, and we always wanna follow the first law of thermodynamics, which is whatever Q you have, so Q1 plus Q2 plus Q3 plus whatever processes are happening, there is never any energy lost or created. So we're gonna say that that's zero because we don't have no energy can be created, no energy can be destroyed, everything is conserved. So it's the conservation of energy, the first law of thermodynamics. And our Q's here are gonna be the Q for the water, whatever's happening with the water, plus the Q for the metal, and that equals 0. Now, I know that we're gonna have some, in our situation, there's gonna be some heat lost out to the environment, but we're gonna assume that anything, so let's say I have Q environment, okay? But we're gonna assume that this is negligible in this case. We try to make this as negligible as possible because we have an insulated container. I know we normally would have a cover on it, but it happens pretty quickly. And just to make the calculations easier, we're just gonna deal with these two things here. And for most chemistry classes, you're not gonna have to worry about any extra heat lost or gained from the container. So we're just gonna worry about the water and the metal. So now what I'm gonna do is I'm gonna set up, I'm gonna make these equal to each other because we need to solve for something. So I'm gonna make my Q metal, so if I subtract Q water from both sides, so I subtract Q water, so now I'm left with Q metal equals negative Q water. This negative sign only comes into play when you have, because I have a temperature change as a drop here, and I have a temperature change as an increase here, we need to have a negative sign to kind of accommodate for that. But remember, if I'm solving for something called specific heat capacity, heat capacities can never be negative. So what am I going to set up here? Well, Q water, I know that Q from my equations before, Q water, sorry, I just wrote it again, equals M water times C water. C is the specific heat capacity, M is the mass, times the delta T for water. Delta T is T temperature final minus temperature initial. So let's go ahead and plug some of these numbers in to get this quantity. So this is, M is going to be 82.91 grams. C, I didn't give you up above, but C for water is going to be 4.2 joules per gram degrees Celsius. This is from a textbook value. So water, I should have just said in the beginning, we know a lot of stuff about water. We can measure everything about water, but we can't measure heat directly. However, we can measure changes in temperature, and because we can measure the change in temperature for water, we can figure out how much energy is going into the water. So that's what kind of this lab is about. We use something we know, which is water, to figure out something about the unknown, which is the metal. And then T is my change in temperature. It's always the final minus initial, so 24.2 minus 20.9. So this is final minus initial. Okay. I'm going to go ahead and plug that in. See what we get here. 82.91 times 4.2 times my temperature change is 24.2 minus 20.9. That's 1,149. I'm just going to round it to that. And this is going to be in joules, because this cancels, Celsius cancels, Celsius, that cancels out. And we're left with joules here. Okay, so this is the energy going into the water. That's how many joules are going in. Now I have a negative sign here because that's going to, you'll see later that on the left side, we're going to have a negative value. The negatives just end up canceling out, so you don't have to worry too much about that. Just want to get the numbers. But heat does have direction, so you can have energy going into something and energy coming out of something. So it is important to kind of keep track of what direction energy is going. So now I have the energy going into the water, but that energy comes from the metal. So Q of the metal is going to be the M of the metal times the C of the metal times delta T of the metal. Okay, we know these two values here. So let's go ahead and plug this in to see what we get. M of the metal is 57.27 grams times delta T of the metal, which is final 24.2 minus 100 times C of the metal equals this value here. Okay, it's my numbers got offlined. Well, this value here, if I take 24.2 minus 100, that ends up being a negative number. That's where that negative comes into play. So negative 75.8 times 57.27 times C. So multiply this out. And that ends up being negative 4,341. Okay, I'm going to round it. I'm going to use 4 significant figures times Cm equals negative 1149 joules. Well, now how do I get Cm by itself? You can see the negatives are going to cancel out, but I'm just going to divide both sides now by the 4341. Okay, so this gets rid of that. And then now I have my C to equal. So 1149 divided by 43.41. Sorry, 4341 my negatives are gone now. Okay, so that equals 0.265, and this is joules per gram degrees Celsius. My units here are grams and degrees Celsius. So this number here is 4341 grams degrees Celsius. That's where I get my units for the bottom of the specific heat capacity. So this should be my specific heat capacity for this metal here, which is copper. And I'm gonna go look up the value for copper in a second, and I will come back to you after that. Okay, so I just looked it up, and the specific heat capacity of copper, this is a piece of copper right here, is 0.385 joules per gram degrees Celsius. Not perfect. Obviously, it's a little off. We didn't get enough heat transfer somewhere, but I mean, we're losing some energy to the atmosphere, of course. But yeah, I mean, it's not too bad. And I've done this experiment several times where the metal specific heat is closer. So whatever you get, that's the principle of this experiment. I hope that helps.